All right, let's take a look at if compounds are acidic, basic, or neutral. In this case, we'll take a look at salts. So remember, salts are combinations of a cation, positively charged, plus an anion, which is negatively charged, right? So we have our cation, that's some kind of positive charge, and then the anion, which has a negative charge. The anion will, or the cation will always either be acidic or neutral, right? So it's either going to act as an acid or act as basically nothing. And then the anion can be either basic or neutral, right? So the anion can act as a base or it can act as basically nothing, right? It can do nothing in this equation. And so let's take a look at some examples. So first up, we have sodium chloride, right? Sodium does not have an H plus and is not our iron or aluminum 3 plus, so it overall is neutral. What about chloride, though? Chloride, if you're thinking about it, chloride is the conjugate base of HCl. So if chlorine, or if this chloride gained an H plus, it would form HCl. If we think about HCl, it is a strong acid. So this is a one-way arrow. So we cannot go in this direction, right? We can't go in this direction. So this chloride cannot act as a base. And so this too is neutral. And so if you have two components that are neutral, you are overall neutral. So if you just put some sodium chloride in some water, it will not make the solution acidic or basic. Let's take a look at another example. Here we have sodium fluoride. So we already covered the sodium. This is neutral. And then here we have the fluoride. If you think about fluoride, that is going to be the conjugate base of hydrofluoric acid, and hydrofluoric acid is a weak acid. So in this case, we are indeed allowed to go towards the right side of the reaction. And so the fluoride can pick up some H pluses, and so it can act as a base. So this part is basic. So if you have one component that's neutral and one component that's basic, overall your salt will be basic. Let's take a look at another example. Here we have FeCl3. Remember our iron 3 plus, that's one of our examples of the small positively charged metal cations, and these can indeed be acidic. Right? So iron is acidic. If we think about these chlorides, chloride is going to be the conjugate base of HCl. HCl is a strong acid, so this chloride is actually not allowed, this reaction can't go to the right side. The chloride cannot pick up an H plus. So overall, this component will be neutral. So we have an acidic component and a neutral component, so overall we are acidic. Another example here, NH4Br. So here we have, if you think about this, is NH4 plus. This is our protonated amine. And remember, we said protonated amines can indeed be acidic, right? So we have this NH4 plus. It can indeed give up an H plus. So it can indeed act as an acid, right? So it's acidic. If we think about this other component, Br minus, that's going to be the conjugate base of hydrobromic acid. And so again, this is a one-way arrow, so this bromine cannot pick up an H plus, and so overall it is going to be neutral. And so we have an acidic component and a neutral component. Overall, we're going to be acidic. Let's take a look at one more example and a more complicated example. We have NH4NO3, ammonium nitrite. And so if we think about NH4, this can indeed act as an acid, right? NH4 can donate one of its protons. Right, so we have an acidic component there. And then if we think about nitrite, nitrite is going to be the conjugate base of nitrous acid. which is indeed a weak acid. So we are allowed to pick up a proton and act as a base. So we can see in this salt, we have a component that's acidic and we have a component that is basic. So what is our overall salt going to be? So to figure this out, we need to look at the pKa, Ka, Kb type of stuff to determine which component is stronger. So look at Ka/Kb or pKa/pKb to determine which is stronger. And remember, we have the higher K, that's going to be stronger, or the lower pK is going to be stronger, right? So if you take a look at ammonia, if you do some Googling, you'll find that the pKa here is 9.3. If you do some Googling, you'll find that the pKa of HNO3 or HNO2 is equal, there should be a 2 up here as well, is equal to 3.16, right? But that's the pKa of the conjugate acid. What we want to talk about is nitrite, not nitrous acid. And so we can remember that we can solve for the pKb of a conjugate base. Remember, 14 is equal to pKa plus pKb. So we can plug in that 3.16 into the pKa, and thus we can solve the pKb for HNO2, or just NO2 minus. And we get a 10.84. We see that in this case, the pKa is smaller than the pKb. And remember, with the p's, the smaller number means stronger. So the acid is stronger than the base. And so we are overall acidic.